why not? For some reason last year I showed this video, I guess because it was because it had recently happened. Since this is kind of an energy-related class, this was a cataclysmic energy-related disaster in February the 7th, I think it just said, in the Himalayas last year, 2021. And you know, you can make these connections with global climate change, etc. I'm not sure this was, but at the time it was touted, glaciers melting, and what it was a rock slope that failed up high in the Himalayas above this hydroelectric dam that was being developed. The boulder, I mean, it was more than the boulder, it was a huge slab of the mountain, dropped off, landed on a glacier, and then moved the glacier down. With the motion of the glacier, melted it from frictional heating, and just sped down the mountain at super high speed and into an impoundment behind a hydroelectric dam that was being built right now. And you saw some people being dug out, killed certainly 100 people were lost in it. And so one of the big issues these days in terms of the energy transition is dispatchable energy. Of course, baseload geothermal is eminently dispatchable and can spin up quite quickly and is used in that way in California. Hydroelectric dams and pump storage are also kind of in that zone as well. Of course, there are inherent risks in any mode of energy production, and often touted the opposition to, say, nuclear power, but everyone touts the fact that certainly many more people have been killed in dam disasters involving collapsing dams, overtop dams, accidents related to them, than in nuclear accidents, which have been quite memorable. 3 Mile Island, Chernobyl, Fukushima. But the number of direct deaths are relatively small, and it's not clear exactly what the number of indirect deaths would be in those cases. 3 Mile Island, relatively small. Fukushima, I think, relatively small as well, but there's a bunch of young people suing, is it TEPCO, Tokyo Electric Power Company, for effects on their health 11 years afterwards. The Tohoku earthquake was in 2011, March of 2011, so almost 11 years afterwards. And so, anyway, this just struck my my fancy a year ago. I notice every day before I come to these classes, I look at our recordings and run them at 60 speed just to see what we've looked at in the past. And so this was exactly, came up on that. So hydroelectric is one method to be able to both generate electricity, but perhaps more importantly for the renewable energy transition is to provide storage. You know, pump storage is a way to do that. And the other thing that came up, I guess, which I thought was kind of curious, was this idea. And this is the idea, it's out of the UK. One of my friends sent it to me. I thought it was kind of interesting. So the usual idea is you make hay when the sun shines, so you generate power from PVs in the daytime, not at night. Wind power when the wind blows, and then you store that electricity by pumping water up into an upper reservoir when it's either available during the daytime or when you have cheap energy at night, potentially, from nuclear power, which runs all the time. And then you run it back down through the system at night, in the daytime when you need a quick spin up of energy for everyone's toasters. And so it can be on a pretty tight diurnal. It's really diurnal for daily use, different parts of the day. This is an idea to do something, since you know that the amount of power you get out of this is proportional to the mass flow rate times the head times the density of the fluid, which I guess is embodied in the mass flow rate. But if you wanted to, for instance, instead of using water, which of course has only a single density and unit weight, you could use a much denser fluid. In which case, if you pump that denser fluid up into some tank, probably a smaller volume of it, and then allow that denser fluid to come down through the turbine in the same way between a closed system, instead of being perhaps an open reservoir and an open reservoir, they're closed upstream and downstream tanks, then you can get the same power output from it just by virtue of the fact that you're using something that's a slurry that perhaps is 3 times the density of water. You could use a slurry that's laden with barite or something. So I'm not sure exactly what they're using. I didn't read it. Do you see what it is? A new startup to do this stuff. I don't see what the fluid is that they're using. But anyway, you get the idea. So that's just backing up to talk about the things that are peripherally related to this class. Since geothermal can be used as a base load power to generate all the time, or it can also be used to spin up to be able to fill in to the grid as needed. Okay. So I did go through your stuff last night. Thanks for your submissions. I just went through it at 9 or 10 o'clock last night, just quickly. Don't read too much into the comments. I felt obliged to make some comments just because you'd submitted some stuff. I'm not sure what I'll do when you submit your outlines. I'm not sure whether I went through them last year or not, but I certainly gave some comments based on the submissions that we've made. And so I won't go through them, but they're all over the place, fine. One person mentioned 2 alternatives, so it didn't interfere if too many people were doing something. That doesn't matter so much. Although ultimately, since you'll view them all, you don't probably want them all to be exactly the same topic. And so you'd have received my topics. There's a couple of non-submits, but that's no big deal, I don't think. And so I think everything's in order. In terms of the schedule, I guess the schedule is such that maybe in 2 weeks' time. So that was this past Sunday. So I guess 2 weeks from now, you should upload. They're all on Sunday evenings. There's no real deadline attached to them, but put it in your mind. So it's just a logical succession. Prepare some kind of outline. If you want to change your topic, I think it's no problem doing that. Then prepare the presentation in PowerPoint form. Narrate it. It's easiest, and actually there is online on our course resources page. If I go back to one of these, where would I be? If you go onto our course resources page, I'm guessing there's a movie to tell you how to do it on PowerPoint if you haven't done it. It's very simple. You just make your slides in the normal way, and then you can record your narration. It's actually very good because it allows you to be able to, why don't I run it just so you can see it. So if you haven't done it before, you'll see that you can record your narration to each of the slides. And I'll see if it does it. Yeah, so it allows you to hit the button, record what you want to record. It keeps it in PowerPoint. You can pause it, you can go back, you can erase that slide. If you made an error, you can change it by just re-recording the single slide, and you can build up your presentation from that in a pretty straightforward manner. And so I'm certain you're not no strangers to making presentations, but that's a useful way to know how to be able to put them together, narrate it in PowerPoint, and then you can convert it to MP4 as one of the export functions, which is pretty straightforward. So there's some notes on how to do that, pretty straightforward. I imagine you're all very skilled at that. And so the schedule that we have is this. And so I guess really by narrating it by week 9, providing some questions for 11, I'll upload those questions, and then you can do the presentations. I guess we have something, I haven't counted it lately, we have 20 or 23 people in the class. So you'll end up being a little bit busy in that last couple of weeks, but I think it's not such an onerous task. So anyway, I think the deliverables on this class are pretty straightforward, pretty easy. All right, so that's that. So I'll get rid of that. And, well, don't want those, but I do want this. Yeah, this is good. You've seen this before in your past. If you had 303, you've certainly seen it. So we've talked in this class that geothermal energy, we know that ubiquitously there's heat under our feet. We know how quickly it rises with depth, and you should have those numbers stuck in your head. I don't know if you can put this in auto loop form. But to be able to recover it, we need to be able to access it somehow. And typically for open loop systems, unlike ground sourced heat pumps, which use a closed loop system, open loop systems require us to use something as a heat exchange fluid. It could, of course, be the water that's or the glycol that's flowing in the heat pumps coils, or it could be the fluid, whatever that is, that's in the Endeavour system that we looked at in Rocky Mountain House, Alberta, a couple of weeks ago. Or it could be the fluids, the native fluids which are present in geothermal reservoirs, which we want to tap. Or it could be fluids that we put into those geothermal reservoirs that are relatively low permeability, low porosity, and that we enhance that to be able to make it into basically a geological heat exchanger. And so the behavior of that heat flow fluid as it comes through the crust, taking heat and moving through the system, is the essence of geothermal energy. And so that's what we're interested in finding out about. And so this just happens to be, if you haven't seen it before, it means you didn't come to class, 303. This is just I guess, promotional video from a company called Ingrain. They got bought out by Halliburton. Their whole idea was that to be able to figure out how quickly you can drag gas shales out of the subsurface, one important parameter to know is the permeability of the material. Difficult to be able to determine, but one option is to be able to take the chips that come out of the cuttings that come out of the drill hole that get blown out by the air flush if you're using air. Take those chips, X-ray CT them, and you see these little grains here. This is probably a synthetic example, but certainly you can get the architecture of the pore space by CAT scanning it. And then you run a sophisticated numerical model to be able to see how quickly you can transfer, whoops, I didn't want to do that. You can transfer fluids from upstream to downstream, and that's a measure of the permeability. And so you can do this virtual experiment to never having run a physical experiment to measure the permeability, but being able to assemble it from the architecture of the pore space, the sizes of the capillaries which control the rates at which you can drive fluid through under a given pressure gradient, just like driving flow down a pipe. But these happen to be lots of individual pipes with different morphologies, and you can come away with it in terms of being able to evaluate exactly what the permeability of the system is. So that's what we're going to kind of have our foray into today. And so that's our plan. So what we'd like to be able to do is be able to move on from the things that we've talked about to be able to make the logical next step. And so you know all of these things. Fluids present naturally are introduced, a function of heat transfer in the medium. We know the heat transfer, we know the heat distribution in the system. It's this gradient in space that goes down at 25 or 50 centigrade per kilometer. The most efficient form of transport for us is convective heat transfer. Don't break on me. Okay. And so we know that. And so that will be useful for us. And that the fluids that are present in there may be naturally occurring water or brine, or they could be artificially induced for us to be able to recover heat. As I said, it is a big geological heat exchanger. We've made the case that the power that you can get out of this is equal to the volumetric flow rate, the density, the specific heat capacity, and the temperature drop between the reservoir and your ejection temperature. And so this means you need to get water out at some significant temperature drop, 200 degrees centigrade perhaps if you're lucky. The density of the fluid that carries it doesn't vary very much. If it's water or CO2, actually they're within a factor of 2 of each other, and also the specific heat capacities. But if your flow rate that you get fluid out of the system at is slow, then this is the rate limiting parameter. So the flow rate and the heat drop are the 2 rate limiting parameters. It might seem that the heat temperature drop isn't really a rate limiting parameter, but it is. You might think it's not, because if you go down for 4 kilometers at 50 per centigrade per kilometer, then you know you're at 200 centigrade by the time you get here. But whether you can bring that 200 centigrade in the water that comes to the surface is another matter, because it relies on the fact that you have a large geological surface area for it to gather the heat from. And so you want to have high through flow. We've said 100 kilograms per second to be able to pay off the $10 million for a well, and to get 5 megawatts electricity out of it. And to do that, the water has to be coming out hot, 100 degrees centigrade. And so that's what we will talk about. So I guess the things that we might want to say something about: what controls fluid movement? And the punchline is that it's mediated by 2 properties. Permeability perhaps is the most important. Storage may be the second most important. So permeability is a measure of volumetric flow rate as a function of the pressure drop between injection to recovery. And so this is one parameter that we need to know in great detail. And storage says something about how fluids are stored, the accumulation term, if you want. Much less important for us in understanding this. We need to know this behavior for multiple phases. And so you remember from what we've talked about, if again we draw it in microcosm, if we draw this as enthalpy, which we defined as internal energy, pressure over density, is that right? And something like either temperature or pressure, doesn't matter which. Then we have this kind of phase diagram that brings in fluids that come in at some temperature, go across here, and scoot off down here. And so we have this phase diagram. And I guess the only important thing about this phase diagram for our interest right now is that as we traverse it, we know that we go from these regimes, which are, this is 100% steam, to 100% liquid. And we went through this brief example last time to say that if we come if enthalpy doesn't change, delta H is 0, we end up at some point on this curve, and we know that this is 75% liquid and 25% steam. And so the fact that we have 2 fluids within our reservoir means that in transiting across the reservoir, we have to worry about the fact that we have more than one type of fluid to worry about. And so the multiple phases is something that is a given for us. And I guess this is the term that we just described up here. If we want to be able to get heat out of our reservoir, and we think that this term Q is a volumetric flow rate, it's going to be a fluid flow velocity times a cross-sectional area times a permeability, viscosity of the fluid, and a pressure drop. This is Darcy's law. And it's a little bit like if you divide both sides by area. This is kind of the flow within a pipe. We'll go through this. This is just giving you a taster for this. This would be the cross-sectional area of flow. It's really not very different from our heat flow rate, which we said was equal to thermal conductivity multiplied by temperature gradient in space. And so if we have a temperature gradient from upstream to downstream and drive it through thermal conductivity, this gives us a heat flow rate out of the end of this core. If we have a pressure gradient, a drop in pressure between upstream and downstream along a length, a permeability and the property of the fluid, that gives us Darcy's law. So this is Fourier's law, right? And you already know that mass flow is equal to diffusion coefficient times change in concentration dx. So Fick's law, Fick's second law, I think, right? So you'll have seen these. Not belaboring the point, but only to make the point that your education should kind of broaden you. And so these essentially are the same laws. They link a first order derivative to a quantity of flow through a coefficient. There's a negative sign here in all of these because the direction of the flow is in the opposite direction of the positive gradient, which we've talked about as well. And so what we will do today is we'll try and figure out exactly what this parameter that defines the coefficient of efficiency in our system. And I guess you also know Ohm's law as well. V equals IR. I guess you could write that in a different way as I is equal to 1 over R V. Voltage, current, potential voltage. Voltage is a drop between 12 volts between upstream and downstream. So it's actually exactly the same. It's just that it's kind of not in this differential form, is because you usually measure it over a resistor, right? You have an upstream up current, up gradient current, down gradient, voltage. And that voltage drop, delta V, defines how much current you can get as a function of 1 over resistance, which you could think of as a conductance. 1 over resistance is a conductivity, which is a bit like a permeability. So Ohm's law, Darcy's law, Fourier's law, Fick's law, they're all essentially the same. They relate a gradient of something to a flux of something. Electrons in the case of electricity, I guess. So, suitably impressed by your newfound broad-scale knowledge, let's talk about flow of transported fluids. And so this little presentation, I think this sheet will split into 2 days, so we won't go through all of it today. But we'll try and make a start on trying to understand it in a big picture. And so the idea is basically this. If you take a porous medium, just like the block that we looked at for the in-grain video, and you can imagine that porous medium being what we would call an REV, representative elemental volume. Elemental volume. The idea is that you take a volume big enough to have enough grains that it's representative of the rest of the reservoir. And so in looking at this would be the box that outlined the in-grain movie that we looked at. And these would be the flow channels which would allow different fluids to travel. And so if we have 75% water and 25% steam, as we just alluded to, then if the steam is the green one here, let's do it. So we can define these as some parameters. We can define the porosity as being equal to the volume of voids divided by the total volume. I guess I always used to write into this. So the volume, the total volume would be this volume here. So if it's 1 centimeter by 1 centimeter by 1 centimeter, it would be 1 cubic centimeter. And the volume of the voids would be the pore space that's within that, which we could measure in some way. So we can define the porosity, which is that. We can also define the saturation. And we'll call that S for the water saturation or the wetting saturation. And we define saturation as the volume of water divided by the volume of the voids. And so if this is 100% water filled, then the saturation has to vary between 0 and 1. So if you only have one fluid and it completely fills the system, the saturation would be 1, and this would all be red. If the saturation of water was 0, then it would all be green. And we can define 2 saturations, each of which run between these boundaries. each of them, when we add them together, have to equal 1, right? Because there's no pore space other than that. And as we look at the variation in those properties, we can exchange one for the other. And so if we think about regularizing this by, for instance, centrifuging it so the non-wetting fluid is present within our system in one location and fills all the pore space, and the wetting saturation is elsewhere, then the proportion of these would be essentially the saturations. So in this case, the non-wetting saturation would be, I don't know, 25%. Actually, it's quite useful because that's exactly the numbers that we used before. And the saturation, perhaps in this case, would be of the wetting fluid, which is equal to 75%. And so it's important for us to understand what we mean by the wetting saturations. And what this means is that if we have a fluid and we take the red fluid and we put a capillary tube in it, then what would happen is that the wetting fluid would rise up, and it would rise up to some height, and we already did the calculation for this in 303. The height rise would be something like 4 times the interfacial tension divided by the diameter and the unit weight of the wetting fluid. But if conversely we had the non-wetting fluid, then a classic example for us in fluid mechanics in that class was mercury. And the idea of that would be that the meniscus would be this. It would be HC. It would conform to the same, actually I'm not going to go there. It would be, the difference between these is that this is hydrophilic and this is hydrophobic. So this is hydrophobic, Greek for hate, I guess, right? I didn't want that at all, come on. And this would be, didn't change. Double L, I'm guessing. So this is what would be called water wetting. And this would be water non-wetting. So I've been quite consistent with my use of green. NW is non-wetting. So in this case, whatever the green fluid is a non-wetting fluid. In our case, let's call that steam. And the red fluid will be water, liquid. They're both water, I guess, right? So it seems that if we're trying to flow fluids, we have to worry something about the proportion of the porous medium which is hosting that particular fluid. So the idea is this. We could think of our little cube of rock, porous rock. In this case, if we think about injecting steam into it, which is our green fluid, our non-wetting fluid, right at this moment, steam can't flow. If you draw a connected path between the upstream and the downstream, you can't draw a connected path which is green. And so what you'd have to do is you'd have to inject the non-wetting fluid to be able to build up the proportion of this area which is filled with the green fluid. In other words, the saturation of the non-wetting fluid would have to increase. If the saturation of the non-wetting fluid increases, then at some stage you get a connection between upstream and downstream, and you can flow both fluids, both the red fluid, water, and the green fluid, the steam, through the system, until if you keep on raising the amount of the non-wetting fluid in each of these, right? Each of these has an increasing of the non-wetting fluid, which is increasing as you go from 1 to 2 to 3. Now all of a sudden you have the opposite system. Now the upstream and downstream are not simply connected by water, liquid water, and therefore the only fluid that you can have flowing within this system is going to be steam. And so clearly, if we want to know the rates at which we can transmit fluids through this system, it matters what the initial state is in terms of where we're sitting in here. This defines something about our fluid transmission characteristics. So that's why we have to understand this. And so that's what we'll attempt to do. And it's really quite straightforward. And it's explained kind of in this, which I will draw on. I think I can explain it much better. Well, actually, it's not explained too badly there. But let's imagine that you want to draw in perspective. I'm going to draw. So this is our sample that we have upstream pressure here. A downstream pressure. And so this is a gradient, right? This is dP and this is dx. This is our coordinate direction, and this is also what we've referred to as Q equals, stop it, fluid flux, which is in units of velocity, meters a second. I'm not sure what I'm doing wrong, but it wants to grab this all the time. Perhaps the Bluetooth connection's slow. And this is essentially what is going on. So in other words, if you want the velocity of this fluid that comes out of the system, you need to multiply it by a pressure gradient between the upstream and downstream over a particular length, which is shown here. And the rate at which it comes out is given by the velocity of that fluid, which is defined by its permeability. This term, I guess, is defined below. This is effective permeability. And so this is Darcy's law. Flow velocity equals pressure gradient dP dx multiplied by permeability and divided by the fluid coefficients. This is the permeability that it sees, but of course it's perhaps easier for us to write it in the terms of that within each of these each of these fluids, fluid 1, which is the green one, which I guess was our steam. This is non-wetting steam, right? And this is wetting liquid water. The idea is that permeability is an intrinsic property of the medium. So this whole core has one permeability and one permeability only. It doesn't matter if it's flowing steam or water or treacle or CO2. There's a single number. It's 10 to the minus 18 meters squared, which is the units of it. But what is different in each of these is that the water would have a viscosity of 10 to the minus 3 pascals a second, and gases maybe 2 orders of magnitude less than that, or smaller, so it flows faster. So that's the only difference in here. And so what we could do is we could write that the volumetric flow, say, of the liquid water, I'm going to go, well, no, liquid steam, Q1 is equal to A1 multiplied by lowercase q1, which is if I just substitute this, k1 over mu1 dp dx. So dp dx is this term here. And so this has to be pre-multiplied by A1. But it's not so obvious what A1 is. But it is kind of obvious if we think about plotting up, for instance. If we plotted a graph of essentially these cross-sectional areas are surrogates for the relative saturations. So if we centrifuge this down, we said that this proportion here is 25%. So we'd expect the saturation of the non-wetting fluid to be about 25%. And this is 75% for the red. So we'd expect that. So in some respects, if this is the cross-sectional area of flow coming towards us, we do have some kind of idea of these areas. So what we could do is we could replace this. The easiest way would be just to replace A1 as equal to the saturation of 1. Right? Because we know that when it's 100% saturated with the red fluid, all of the area will be covered. When it's 0% saturated with the red fluid, 0 of the area will be covered. And those saturations will scale directly with this area. And so that's one useful way for us to think about it. The other way for us to, so as a result of that then, our volumetric flow rates for these two systems would be equal to, I'm just doing it with these components added. Just write it down longhand. It's the same pressure gradients between upstream and downstream. And actually in this, if I wanted to, I said before that there is no specific permeability 1 and 2 because permeability is a property of the rock and therefore it's the same in each of these cases. So we can think of it as being 1 or 2, but we don't have to. The next thing that we could do, and I'm not sure if I've got the space, I'll do it up here. Let's draw a figure. And that figure will be on the bottom. We'll define a saturation of water between 0 and 100%, decimal 100%. And what we could do is we could plot on the vertical axis, we could either plot area or we could plot saturation. Seems kind of silly for us to plot saturation when we have it on the bottom axis, but let's do it anyway. So we could plot the saturation of water between 0 and 1. And we know if we're plotting water, if the saturation of water is 0, in other words, this is all green. Yes, this is all green. Then the saturation of 0, 0 will be this point. And the saturation when it's 100% water filled will be this point. And a line between them will be the curve that links them. So that's a valid curve to represent that. We could also represent on this curve the saturation of water and how it changes with the saturation of the non-wetting fluid. And the non-wetting fluid driven between 1 and 0. So if the saturation of water is 0, it means it's 100% non-wetting green fluid filled. So that's this parameter here. If the saturation of water is 100% saturated with water, then there can be no green fluid in it. So that's this point here. And so if we join those curves up, we get this kind of X curve. And this curve, it's not very useful to us in this form, but this curve we'll refer to as a relative permeability curve. And I will draw it down here. And this is the basic idea. So the curve we just drew, I could draw it on, I'll draw it on the side of this. The curve we just drew was saturation of water between 0 and 1. Didn't want to do it in green. These are opposite to each other, right? 100% water saturated can be 0% steam. And so the curve we just drew was something that looked like this. Curves, plural. And so what we are going to call it, instead of these vertical axes being either A or saturation, we're going to call this relative permeability. So Kr equals relative permeability. And the idea is that it goes from, to use a neutral color, from 1 to 0, which is what this is. And it means that if we're at a particular saturation, so say, what did we say we were? We were at, so we were at 70, come along, 0.75 or 75% liquid saturation. That corresponds to 25% non-wetting saturation by definition. And all this curve is telling us is that this relative permeability to the system is equal to, for the wetting fluid, the red fluid, is something like, well, it would be in the same proportions. It would be 75%, except written as a decimal fraction. And so, alternatively, for this fluid here, the relative permeability, just from scaling this, just from similar triangles, I guess, would be about 0.25. And so that's kind of the punchline. That is saying that if we want to calculate the volume that we transmit of water in this system, then the volumetric flow rate is equal to the total area of the end of the core so this is A1 and A2, but we're interested in the complete area, which we'll call A. And so we have the area of the core. I'll go back to red. And we multiply it through by a relative permeability of the wetting fluid, which is a function of saturation. So bracket means function of saturation, multiplied by permeability times the viscosity of water times the pressure differential between the upstream and downstream times the length of the core. So that's about as, so this is dP, this is dx, and so you can calculate it. So you know now that our relative permeability at a saturation of 75% water, so this would be 75%, function of, so that doesn't matter. This function gives us this magnitude is also 0.75 in this case. So this would be this would be 0.75. This would be the end area of our core, which we can measure easily. It's much more difficult for us to get A1 and A2, but we can get A as a cumulative ones of those. This would be the permeability of our core. This would be the viscosity of water. I think the viscosity of water is 10 to the minus 3 Pascal seconds at 20 centigrade. I guess it might go down. It might be a lower viscosity by 1 order of magnitude at 200 degrees centigrade or something like that. And this is the pressure gradient. So you have everything you need to be able to calculate the volumetric flow rate through the system. And of course, if you wanted to know that, you'd know that the power is equal to the volumetric flow rate multiplied by the density of the fluid, specific heat capacity, the temperature load, and now for the water, you have this. You know what this is. It's 4.2 kilojoules per kilogram per Kelvin, and this is whatever temperature you can get out. And so that would be the power that you get out of the water in the system. I guess the power that you get out of the non-wetting fluid, the steam, would be the volumetric flow rate of the non-wetting fluid, the density of the non-wetting fluid, which is steam, its specific heat capacity, no idea what that is, certainly would be less, I don't know if it actually would be less, and the temperature change of the non-wetting steam. That's it. That's all it is. So at a broad level, we need to understand something. So it all comes back from the idea that we're going to produce fluids. They have the potential to be different proportions of liquid and vapor in these reservoirs. If we have some idea of knowing what the equation of state is that describes them, which we did yesterday or on Thursday, we came down for adiabatic system, I guess. Enthalpy didn't change. And so immediately, if enthalpy didn't change, we knew the proportions of liquid and gas. If we know the proportions of liquid and gas, we can figure out exactly the rates at which they'll travel through the system, which are given by what we've just done here. In terms of using Darcy's law for these very simple systems, good enough for the estimations in this class. And if we know what the permeability of our system is, which we don't know, but we'll look at. If we know what this is, then we can calculate everything in here. And so we should probably make a note that K equals a function of rock type only. And so the permeability, as we define it, is a function of the rock type. And so you might have realized also, so that's kind of the way that we think about this. So if we can get the relative permeability magnitudes, if we know the saturation, then we can do that calculation straight away. The reality is that the relative permeability figures don't quite look like we've drawn them as this idealized X plot. And I suppose if we wanted to, we could change our figure a little bit by realizing that it might want to look a bit like this. Of course, the figure doesn't quite look like this either. So we could modify our X plot to look like this. And the characteristics of this are quite easily explained in a physical way. And that is, if you have a steam-dominated reservoir, mainly 75% steam. Well, let's actually go back from the case we are. So we're in a liquid-dominated reservoir. We have 75% liquid, 25% steam. So this is the case where we are. Red is the liquid. So it means that, at this case, between upstream and downstream, we don't have a connection with the green fluid. So by definition, the relative permeability of that fluid must be zero, because it can't transmit. And so instead of being this X plot, which at 25% would give us a finite value for this relative permeability, it probably, in a straightforward way, should more likely be this point here. And so the real magnitude should be down here. And that will occur until we get enough non-wetting fluid in the system until the steam is a continuous phase from upstream to downstream. Once it's a continuous phase, then the relative permeabilities of the two systems, well, this is 50-50. They're almost the same as each other in this particular case, which would kind of make sense, I guess. Put more steam into the system, then the liquid saturation goes down. At some stage, the liquid saturation snaps off. Red is not continuous from upstream and downstream, and therefore you'd expect that the relative permeability of the red fluid would be zero. And so instead of having this X plot that goes into the ordinates of our graph, here, 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 and here, we'd expect it to be an X plot that is in the ordinates of the graph but excludes these kind of no-go zones which we can't go into because we can't get transmission from upstream to downstream. So the reality is that these relative permeability graphs would be restricted to the so-called zones where we have SW0 is defined as the irreducible saturation of water. of the wetting phase. I guess in our case it's water. And SNW0 is the irreducible saturation of the non-wetting phase, the steam. And what this is saying is that no matter how you try, if you try and fill all of your pore space up with steam by going to the left here, you can't do it because you get little pieces, blobs of water trapped in there which you can't get out because they become isolated islands. And try as you might to push more steam in, it just goes around those islands and out the other side. It doesn't actually change their saturation. And so you have an amount of water which is always left in the system. And by the same token, if you go in this direction, putting more and more red fluid, the liquid, into the system, you end up a place where the steam snaps off as individual islands, and pushing more water in the system just goes around them and out the other side. And so that's the essential deal. We could do much more sophisticated things with this and look at the behavior in these zones, but we don't, I think, need to for this particular class. The other thing which is worthwhile noting is if you add these two curves together, the green curve and the red curve, you get this dashed curve here. And so it turns out that it's not equal to 1. And so certainly if you added these two linear curves together, you'd end up with 1. Certainly if you added these two linear or bilinear or trilinear curves, I guess, right? Horizontal, inclined, horizontal. This trilinear curve, the green and the red together, you'd also end up with a curve along the top, which was this. But that's not the case when you do this. You end up with a curve that looks like this. And so the physics of what's going on with that is that the relative permeability to the steam is higher than for the water, and that is because the steam occupies the big pores in the system. And so the big pathways get occupied most easily by the non-wetting fluid, which just forces its way into them and leaves the smaller ones to be invaded by the liquid, and therefore you get this lopsided behavior. But for this course, it's probably enough to be able to understand the mechanisms in terms of an X-plot with these kind of no-go regions on either side. This is the region that you can't get filled with water. And this is the region that you can't get filled with steam on the left-hand side of this. Right? So, anyway, so that's kind of a potted introduction to multi-phase flow. And the punchline, I think, is exactly this. We can get the volumetric flow rates. So you can check the units for this, but the units for uppercase Q1 have to be meters cubed per second, or volume per unit time. And you can do it by looking at the terms. This is Pascal seconds. This is Pascals as well. So Pascals must cancel out. So you'd be left with 1 over seconds. You're left with length squared, which is length cubed, divided by length, which is, length squared times length squared, which is length to the 4, divided by length, which is meters cubed. And you have no other terms in there. We've got rid of mu and dp, and with this seconds coming up. So it's meters cubed per second. And so the permeability in this is always going to be defined in terms of meters squared, which we'll look at later. Okay? And so we have enough to be able to calculate the volumetric flow rate. The power out of the system is going to be the mass flow rate, the product of volumetric flow rate and density, the heat capacity, and the temperature between the reservoir fluid that you recover and the temperature you eject it to once you've put it through your work machine, your turbine. So that's good. And we can do it for either of our two fluids. You'll find out that because the density of water is 1,000 times larger than the density of steam, that even for equivalent volumetric flow rates, you get much more power out of the hot water. And of course, you can flash that hot water to steam to get the full massive enthalpy out of the system. Okay. All right, so I'll get going. We could do more sophisticated things with relative permeability. I'm not sure we do in the remit of this class. It's not very important to us. We've talked about the relative permeability figures. It turns out also that if we look at these relative permeability graphs, we're going to use this X plot, which just does this, which is convenient for us to be able to approximate it. But if we wanted to use real curves, we'd find out two things. We'd find out that not only are the curves nonlinear, as suggested here, but the curves are hysteretic. And so as you change the saturation in one direction, you go up a curve, and as you come down the curve, again changing saturation. So this would be going, more steam would be going if you're up here, more water is if you're coming down here, or more water content. And so the point is that for any given saturation that you find yourself at, bad English I think, you could define two particular relative permeabilities. And so it's ambiguous as to which permeability you should use, but the difference between them probably isn't huge within the range of the things that we're trying to estimate here. The reason for this is, the most simple explanation I can think of is if you look at raindrops rolling down a windshield. And that is, if you think, well, you should look at one sometime. The leading edge of the raindrop is steep because it's not, this part of the glass has not been wetted before. The tail of the raindrop is shallow because it's been pre-wetted. And so the fact that it's already been wetted versus unwetted means that the contact angle and the ability of the fluid to wet the surface is different. And therefore, that's kind of like this. This one is the tail end and one is the front end of the drop. And it just matters on the history of its wetting of what it sees. But probably not important for any of the things that we're dealing with. So that's one of the things. All right. So implicit in this is that this is the calculation we're going to want to be able to do. So if we want to get the volumetric flow rate from this equation, we need to know something about what this term is for permeability. So the question is, how do we get that? Well, clearly, what we could take is a core in the simplest way, right? We could write, if we just had one fluid, we could put the equation together like this. We could apply an upstream pressure, a downstream pressure. We know how long the core is. We could multiply both areas on either side. We could measure the volumetric flow rate that comes out if we only have one fluid. And so we can measure this. We measure it over a period of time. We know the pressure we apply. We know the length of the core. We know the area of the core. We know the viscosity of the fluid, single fluid we're flowing. And the only unterm we have is this. So that would be a relatively straightforward way to do it. And that's exactly how it's done, of course. And so we could take a core to a lab, apply a pressure between upstream and downstream. I think that's exactly what this thing is showing here, but for a more complicated way. You have a sample, upstream pressure, downstream pressure, gather the downstream flow rate, measure it over a period of time in your bucket, and you have a measure of the volumetric flow rate. You could also do it with two fluids. You could do it with oil and a gas, and that's exactly what this apparatus is showing us. So you could do it in the modes that we've kind of alluded to, in that you could do it when it's at different saturations. So you could do it at saturation of the non-wetting of 75%. You could do it at the saturation of the non-wetting, or saturation of the wetting, at about 75%. Obviously this will be 25% wetting, etc. Because they have to add to 100%, of course. And you could do these experiments, all these. But it's much easier just to do it for one fluid in the sample, completely saturating it, and you get a single value for this property, which is a measure of the transmission characteristics of the core. But you could also do something a bit more sophisticated, and it actually kind of impinges on what we looked at with in-grain. And the idea is you could do a virtual experiment. So what you could do is you could take your in-grain cube. You could imagine that it has a bunch of capillary tubes running through it. The cube is, 1 centimeter, 1 centimeter, 1 centimeter. And these individual tubes are of some diameter, d. I guess this is diameter d, lowercase d. And if you know the equation for flow within a single pipe, if you cast your minds back, the average velocity of the fluid coming out through the end of this pipe, and so if we had a pipe, then I'm certain you all remember that the velocity profile is parabolic and would look like this: 0 at the edges and maximum in the middle. But if you transform that to being an area of flow which is the same area of this little thing that I'm drawing here as this would be U bar, and this would be U, right? So U bar is just the average flow rate per unit cross-section. Pressure gradient, diameter squared, viscosity, same as before. Pascals, so we're left with meters squared divided by meters per second. So the units of this would be in meters a second. Not that it really matters. And so the idea is this. What we want to do is we want to make our porous medium be a whole bunch of these individual tubes. And so if we know how much fluid is coming out of one tube, then we could get the total volume that's coming out of one tube as being equal to this average flow rate multiplied by the area of the tube. So that's what this is. The volumetric flow coming out of a single tube is just going to be the average flow rate U bar, which is this, multiplied by the cross-sectional area, pi d squared upon 4. Pretty straightforward. And so we know how much volume is coming out of each tube. All we have to do now is figure out how many tubes that we would want to include. And so the way that we can constrain the number of tubes is that if we think about the end of our sample, then, I did it half an hour. I'm going to wind up very soon. You can think of these being the wetted tubes. We know that the porosity is equal to the volume of the tubes divided by the volume total. The volume total is going to be, I guess we've called it dz and dy in this. And the volume of the voids would just be the sum of all the circles. That's all. And so the constraint we do have is going to be the number of these tubes we have is controlled by the porosity. Must make sense, right? The tubes have a given diameter, which we're going to prescribe because we know what the size of the tubes are, the pores. And the number of tubes that we have is controlled by how many it takes to fit into this square so that the porosity becomes equal to what we know it is, 20% or whatever. So that's this. Porosity, volume of voids, volume of total, which is the area of the voids of the area of total multiplied by the length of the sample, right? Area times the length is a volume. And if we multiply those out, we end up being able to define the porosity as equal to the area of the voids, which is the area of a single tube multiplied by the number of tubes times its length. So area times length is the volume of one tube, and multiplied by the number of tubes gives us the total volume of those tubes, and we divide it by the total volume of the cube. area of the cube times dx. So the cross-sectional area of this front of the cube is just dz dx, which is this. And the length of the flow pipe is this. These go out, I guess. We know porosity. We don't know how many tubes we have, but we know what the areas are, and we know the length of our sample. We can rearrange this in terms of the number of tubes. And so if we find out exactly the number of tubes from this equation just by rearranging it, then we can multiply the flow per tube by the number of tubes, and we have the total flow. So this would be, the flow per tube is going to be this. This is Qi, this is the area of a tube, and so these parameters together give us the volumetric flow rate, this whole term here. You'll never have to, well, you don't have any exams in this class, so you never have to reproduce it anyway. And we multiply it by the number of tubes. So if you rearrange this in terms of I, then you just end up with porosity multiplied by dx, dy, dz, and divided by this term and this term, which is what this is. Cross out dx. This goes out with this. We end up with this term here. This term here is the total area of the end of our sample. And again, just to make it simple, as it turns out, the total volumetric flow is equal to the area flow, dx, dz, dy, some term which represents the permeability and viscosity, dp. If we just write it in terms of this term, then we end up with this equation. So this represents the area of our system. This term we have here, and so the one term that's left is equal to this. So it's kind of a long path, but it's useful to do it, I think. Just says this. So if you know the diameter of your pores in your sample, and if you know the porosity of your sample, then you can immediately calculate the permeability, which is in units of meters squared, just by doing this calculation. And it's just it's what we would call a capillary model, because it relies on capillaries that are small tubes that are just pipes running from upstream to downstream in our system. And if we know what the diameters of those are, we have some way of being able to calculate that. If instead of drawing our architecture so that we had single tubes going in one direction from upstream to downstream, if we took it so that we had some tubes going upstream to downstream, others going perpendicular to those, and others going perpendicular to those, then perhaps that's a more realistic model of what's going on, because now we're distributing the porosity between these capillaries that go in all directions. So if you think about it, if you look at now the flow that's going along one of these capillaries, it's only going to be a third of the magnitude of the ones that we had before when we arranged them all in this direction. And so the permeability in this mode is just going to be a third of that magnitude. So instead of 32, it would be 96, 3 times 32. And so it's very simple. And so if you think about it, if we kind of come full circuit, if I still have this open, this is exactly what we have. And so this is a much more sophisticated model of doing this. You can see on this maybe individual grains, so it's kind of a synthetic model that's been made, but you have pathways between those grains, which are complex. They're not exactly tubes, but if you idealize it by tubes from upstream to downstream, and you knew what those diameters were and what the porosity of this, then you could, in one step from that one equation we have, get a pretty good estimate of the permeability of this. This would be the permeability when it's completely filled with the red fluid. And if we wanted to do the calculation when we had a portion of the cross-section which was different from that, then we'd merely have to account for the fact that our relative proportions of that are controlled by another parameter, which is given by this relative permeability. So we can always go back to this equation. Now we've found a way of estimating this very easily. We'll talk about a way to estimate it for fractures next time. And all we need to know is this: the viscosity of the fluids flowing, the pressure gradient that's driving it, and some measure of the relative saturation of fluids A and B in these two-phase systems. And that's it. So that's porous media flow for you in one basic lecture. So next time we'll talk a bit about what these magnitudes might be. We'll talk a bit about what those behaviors might be for fractures, and we'll talk about how we can look at it in a more sophisticated way to understand what transport within our system might be. But we'll leave that for next time. So great.